Oh boy, this can be a real doozy of a problem, but there's a lot of stuff going on here, a lot of things that aren't so obvious, so we'll try and take it a step at a time. This is probably going to be a longer video, but if you can understand this example, I would feel pretty comfortable with anything to do with Amperian path, Ampere's law. So let's get started. So for this question, you have an inner conductor, which I colored purple, of radius A, and it carries a current I in the Z direction. This is supposed to show that the inner conductor here, the purple one, it's got current going in the Z direction, which is, in this case, outside the screen. It comes out of the screen right into your face. And you have this empty area right after it, and that's a non-magnetic material. It's not a conductor. Okay, so nothing really interesting happens there. And then you've got this region. You've got an outer radius B. So let me label that for you. So this is A. This is A. This is B. Okay, and this outer conductor, which is yellow, it's got a current negative I, which goes into the screen, okay, which is what this X is supposed to mean. And this outer conductor has a thickness of T, like that, okay. So, you probably got some bells ringing in your head saying like, okay, there's a lot of regions here to deal with. We should probably break this into regions, and that is how I would start. So let's number these regions. So the way to approach this problem that I think is most intuitive is to use Ampere's law to draw different Amperian paths for all the different regions. So we're going to define our different regions that we're going to draw Amperian paths for, and we're going to use Ampere's law to find H using all of those. So for this first region, we've got, let me show you. In green here, this is going to be the first region's Amperian path, this small green circle, and that is going to be when rho is between 0 and A, like that. The second region is going to be Amperian path of this type right here. It's going to be basically any Amperian path between radius A and B. Also, I should say we're working in cylindrical coordinates. So if this is like, it's like if the z-axis is coming out of the screen, then basically in every other direction, like we're looking at an xy plane basically, so rho is in like every direction from here. The third region, and this is the trickiest one in my opinion, it's going to be any Amperian path that falls inside this layer of flavor here, this conductor here. This is going to be inside the outer conductor, and we'll call that rho's between B and B plus T, right? Because this is radius B right here, and radius B plus T is this length, because this is only T, so this is B plus T. So rho will be somewhere in here, so that's between B and B plus T. And finally, everyone's favorite, not really, the Amperian path outside, okay, and that is simply rho is greater than B. So now that we've defined the 4 regions we're going to be working with, we want to find H for all 4 of these regions using Ampere's law. So let's get started with that. So let me copy and paste this a couple times here actually. Yeah, this is one reason why I like to use the laptop instead of writing stuff down just on some paper and recording that with the camera. I can copy and paste beautiful diagrams like this. Yeah, really sorry that the circles are so messy, but there's no circle drawing tool in the software that I use. Anyway, so we're talking about region 1, which is, we have rho between 0 and a. Okay, fine. So what's Ampere's law? Closed line integral of h dot dl, dl being a piece of the Amperian path in our case, is equal to the current enclosed by this same L, by this same line. So if we're dealing with a path like that, right? This is our Amperian path, this green circle here. Let's evaluate both sides of this, just like how we used to do with Gauss's law, right? So for H here, this is going to end up being H phi, or the phi component of H in the A phi direction dot with dl, and the dl, I'm looking at the formula sheet here, dl for the phi direction is rho dot d phi. So right, because this line, it's going, like, if you take any small piece of it, any small element of it, like this little blue part here that I'm shading in, that's just like a little piece of it, right? That's the little dl of it. It's going in the a phi direction effectively. Okay, and from your formula sheet, if you need a dl in the a phi direction, then you'd use this one. Also because a phi dot a phi will cancel out nicely, and a phi dot with either a rho or a z, the only other 2 choices in cylindrical coordinates, will make this term go to 0, and we know that that's not going to be valid for this case. So the other thing we have to do is write the bounds. This is a cylinder we're talking about, and you'd integrate from phi equals 0 to 2 pi, like this. So once you simplify some of this stuff, you'll end up with, well, once you evaluate, really, you'll end up with h sub phi times 2 phi rho, and that still equals the current enclosed by L, this green circle here. So here's the first tricky part. What is I? I can be expressed with this surface integral with the current density J dot ds. So what can we plug in for J and ds? So J is a current density, right? It's in units of amperes per meter squared. So since the current is uniformly distributed, we can say that J is equal to I, the current going through the surface area of pi a squared in the a z direction. So let's break down where exactly this came from. So this current density J is the same all throughout this purple inner conductor. Okay, and we know that this purple inner conductor carries current I, and that the surface area of this purple inner conductor is pi a squared, right? The area of a circle is pi, right? So the radius of this thing is a, so the surface area of this inner purple conductor would be pi a squared. So that's where that comes from. So this is in units of amps. This is units of meter squared, so amps over meter squared, great. This is in the AZ direction, finally, because the current is in the AZ direction, and we said before AZ is going out of the screen into your face, right? So that's where the direction comes from. And this current density, again, is supposed to be an expression for the current going through that inner conductor, because the current density is the same for that whole inner conductor surface area, right? So that's J. ds is then, by the same idea of more or less of why we chose A5 for here, we know ds has to be in the AZ direction, so we know we have to dot them. And if we dot AZ with A rho or A phi, it's going to be 0, but we know that's not the right value. So the ds ending, the ds in the AZ direction happens to be rho d phi in the AZ direction, right? So once you plug these into this integral, oh yeah, and the bounds should be phi equals 0 to 2 pi, and rho goes from 0 to rho. And it goes from 0 to rho because we said earlier that for this region, rho will be no greater than a. So we can safely say, hey, as long as rho starts at 0, we can let it go to whatever it wants to be, because it already promised us it's not going to be as much as a, so we can just say it goes up to rho. So this is going to be the bounds for this, and you'll plug in j.ds, and then once you do that happily, actually I'm going to scroll to the right, so I'm going to run out of room otherwise. Once you do that, you are going to end up with the I enclosed will end up being I rho squared over a squared, but we're not quite done yet. This is still not expression for h. We said earlier that this is equal to h sub phi times 2 pi rho. So if we divide both sides of this by 2 pi rho, we'll get h equals I rho squared over a squared times 2 pi rho. I'm simplifying this will get you I times rho over 2 pi a squared in the a phi direction. And it's in the a phi direction because we took the phi component of h from before, and that's sticking this a phi in here is how we got our magnetic field intensity to point in the a phi direction. So this is the magnetic field intensity for the first region. Okay, so moving on then to the second region, which is not quite as intense. So for the second region, rho is between A and B, right? And the Amperian path we're going to work with looks like this. So you can save yourself a lot of work here by understanding what's actually going on. And what's actually going on is that the current enclosed by this new Amperian path, remember we said earlier that this inner conductor carries current I. So, and if there's no current in this like black space between the inner and outer conductors, there's no extra current flowing through here. And that means any Amperian path in this region from radius A to B is just going to have I inside of it, right? So then I can say h phi 2 pi rho. This is going to be the same for Ampere's law. This is going to be the same for this whole question. It still equals I enclosed, but we know this time it just equals I, because we know I is the total current that flows through this conductor here. And no matter what your Amperian path is, as long as rho is between A and B, the current enclosed by this big path, this green path here, is going to be equal to I, because there's no extra current in this black space here. So then we can divide this and this by 2 pi rho, and we pop in the bidirection and everything too, and we get this expression, which happens to be as simple as that. That's the magnetic field intensity for this region. Pretty cool, I know. So this is the weird one. Where I just pasted it. I don't know where it went. Okay. My bad. Can't even use the software, let alone teach you field theory, right? So now we're going to deal with what I think is the most troublesome region, the weirdest part of this whole problem. Well, it's not weird, it's just meticulous and really stresses your understanding. So this is region 3, when rho is between B and B plus T. Okay, so remember, B plus T is this whole B plus T thing. B plus T reaches to the outer edge of the outer conductor, and B is the inner edge of the outer conductor. Okay, and now we're talking about this outer conductor, this yellow one right here. And I'm definitely going to take my notes after this. So, as before, let's use Ampere's law. Oh, sorry, let me draw the path here. The path will, the path will look like, it'll look something like this, but more circular, okay? So, Ampere's law apply to this. We have the same h phi, 2 pi rho, is equal to the I enclosed by L. So, now pause for a second here. It's true that we're going to have to use one of these surface integrals again, but that's not all, because the current enclosed by L, it's going to include this term, which is going to be the J and ds for the outer conductor, but there's going to be another term in it. Remember, we're talking about the total current enclosed by this green line, so that includes any current that might be captured by this green line, but from this outer conductor. But that also includes all the current captured by this from this inner conductor here. So this term relates to the current captured from anywhere in the outer conductor, from rho equals B to B plus T. But we also need to add the current I, which is the total current captured from this inner conductor here, this purple one. All right, did that sink in? Okay, so now we need to find Rj for this region. So again, units tend to help me out a lot when I'm not sure what to do. So this is still in units of amperes per meter squared. So surely enough, there's going to be I up here, and surely enough, it's going to be in the AZ direction. So for the surface area here, following the same logic from region 1, now we're worried about the surface area of this outer conductor. So be a little careful, because it's not just a circle now, it's basically a disk. So we need to, for the surface area of this outer conductor is basically pi b plus t squared minus pi b squared, right? So that will get you the surface area of this ring, this donut, this yellow donut here. So written out, it would look like it would look like that, right? And ds, thankfully, is it should stay the same. It should be in the AZ direction for some surface and cylindrical coordinates. So it's still rho, d phi, the AZ direction. So now we can plug these things into here. And the bounds for this should be from phi equals 0 to 2 pi. And from rho equals b to rho. Because rho will be as small as b for this region, but we can let rho go and live freely, let it be whatever it wants to be, because we know it'll never reach b plus t, and it'll stay within this region that we care about. Okay, so then once you use these bounds and you plug in this j and this ds into here, and you add I to it, and you factor a couple of things out, you're going to end up with h phi 2 pi rho equals the current enclosed, which can be then expressed as I times 1 minus rho squared minus b squared over b plus t squared minus b squared. And then from there, as you can probably guess, dividing both sides by 2 pi rho gets you I over 2 pi rho times all of this in the a phi direction. So we're almost home free. This is now we're on to the fourth region, which I think is the most interesting one in a way. I don't even need to really show you the drawing for this. I can just resketch it real quick. This is for rho is greater than b plus t, or basically this is basically now we're talking about an Amperian path outside the whole coaxial cable. So this is pretty cool, actually, how this works out. It's pretty nice. So we had actually might be better. So we had purple inner conductor, right, and we had the yellow outer conductor. And we said from the start of the problem that this purple conductor carries a positive current I in the positive Z direction, and this outer conductor carries a current negative I in the negative AZ direction. So what is the current enclosed by the Amperian path L, which is any green circle like this, which is bigger than, which encloses the whole thing? That's the question. So we know from part 3 more intimately that this purple inner conductor it carries I, and we just said that this outer conductor carries negative I, and well, hey, that's all there is to it. Current enclosed by any Amperian path of rho greater than b plus t is equal to 0. So that means the h for that region is 0 as well. So to summarize, you have h equaling all these crazy things. I'm also going to show how to graph this thing, because that could very likely be a question they could ask, because they asked a similar question on the midterm when we were dealing with potential, electric field, and all those things. Oh no, that's for the first region. And this last one will be I over 2. Alright, Alright, so these are all in the phi direction. And this is how it's broken down in the end. And these are all in units of amperes per meter. So, how do you graph something like this, right? Good question. So, first off all, you should notice what's this function a function of, what variable changes, what variable causes a change, and that is rho. So when rho changes, you get these different functions, and these functions are all always functions of rho. So when you're drawing your graph, wow, that is really bad straight line. That's not much better, sorry. Okay, that's acceptable. So rho is going to be your x-axis traditionally, and you can use h for y-axis. So we have something changes at rho equals a, at rho equals b, and rho equals b plus t. Okay, so let's define these regions here. So for the first part, when rho is between 0 and a, we have basically, if you just put rho to the side, and you take I over 2 pi a squared to be some constant, that basically shows you that this is going to be a linear line. And when rho equals 0, this equals 0. So we can say that we start here, and we increase linearly to some point, rho equals a. And when rho equals a, what does h equal to? When you plug in rho equals a into here, you get I times I over 2 pi a. So you get this milestone here. And then the function changes from rho equals a to b. You get this thing. So you get, if you bring rho out, you get 1 over rho. And if you recall what the function of like y equals 1 over x looks like, it looks like this, right? Thank you, Bethany, for reminding me about that. So applying that here, you would have something that looks asymptotic like that. And at this point, when we switch again, we would sub rho equals b into here. So that becomes I over 2 pi b. Just to show you clearly, we're talking about this point. This point here, this is I over 2 pi b. Now we're on to rhos from b to b plus t. So here, I'm going to tell you right away, I don't know exactly how this thing is supposed to look, but I know it's not linear, and it probably decreases more sharply than this. And I know that at rho equals b plus t, it's equal to 0 forever and always. So I'm just going to approximate it look something like that. And at rho equals b plus t and beyond, it's just 0. It's just 0. And that's more or less what the graph looks like. And that's a question, really. That's a question.